Thanks, Ali. Thank you, Cisco, for having us. Thanks, Christian, also. I believe you guys are sponsors. He didn't tell you that at Georgia Tech, I'm actually in the School of Aerospace Engineering, which doesn't do me an awful lot of good in the video world. So you'll see that later if you start asking me too detailed questions about iframes or bframes. So good morning. You're probably wondering about the title. It's not the usual paper title. This is because today's Friday the 13th. And in the Western world, at least, or in that culture, we associate Friday the 13th with superstition, with black magic. And I thought it's appropriate because a lot of my work on the internet and trying to get cellular connections working or anything like video over the internet is, we call it stochastic and non-deterministic, but we may as well just call it black magic and superstition. So that's where I'm going today. I want to start off and tell you a little bit about Akamai. I know for most of you, I've seen Akamai on your slides. We're basically a little white cloud with CDN in the middle. And hopefully you'll come out of this talk thinking we're a little bit more than that. Our mission is not to be the biggest CDN in the world. It's actually to accelerate innovation in a hyper-connected world and make the internet faster, predictable, scalable, and more secure. And we have business units orientated around those. There's 4 main units: web delivery, app acceleration, security, and then the media division. And I am in the media division, and that's the part I'm going to be speaking about today. We actually have a site up. We collect a lot of data, and we do make a lot of it public. So if you go to www.akamai.com/60seconds, 60 seconds, you're going to see this graphic. It updates with real-time information every 15 minutes. And it shows you, gives you an insight in some of the scale we have within the network. So this is one I just took a screenshot from last week. In 60 seconds, we delivered 2.5 billion HTTP requests. That's about 40 million per second. And if you're also doing the math, every HTTP request generates 2 log lines. That's 80 million log lines per second that we have to collect, gather, and parse in order to be able to build customers. So there's a fantastic amount of complexity just in servicing a network of that scale, and that's on the HTTP delivery side. We stream 7,600 hours of video within that 60 seconds, obviously many parallel streams. So yesterday, and Jason for Google mentioned that between Netflix and Google, they're almost half of internet traffic. Well, Akamai is between 15 to 30% of all internet traffic. And it's fairly safe to say that the majority of the video that is not Netflix or not Google is probably coming from our servers. Obviously, there are other CDNs involved, but we are by far the largest. We also deliver in that 60 seconds 10.4 terabytes of live video. So there's a lot of live as opposed to VOD or on-demand video. Live is always more challenging for a CDN because we've got to deal with replication and latency, and the two are somewhat antagonistic for each other. As soon as you start scaling, how do you keep your latency tight? And this might surprise you. We have 2.8 million active P2P clients. And you probably didn't think or even realize that Akamai has an active P2P network. We have about 30 million peers installed, of which a couple, you can go and see how many are active at any one time. And I'll get more into how we deliver content going forward. So that's Akamai. That's all I really want to say about Akamai today. This is not a talk about Akamai. I want you to think of Akamai as just a cog in the network of companies that deliver content. These are hopefully all the companies that you're part of here today. And we are just one of this ecosystem. And I'm going to talk today about the bandwidth that is growing and the challenges that derive from it, the congestion that's resulting. And then I'm going to look at 10 different technologies that all of us can begin to use to address some of these concerns. Some of them Akamai are involved in, and I'll demo some of those. But most of them Akamai are not involved, but you perhaps are in your companies. So this is our world. We have now an explosion in media over IP, and this stat's a little bit old. So we say we take 700 million users. This is not just US. This is a very conservative global number. 10 minutes of video daily at a megabit. And if you do your peak load, you can probably see about 5.4 terabits. That might be normal on the network. If we project forward a little bit, however, we see the multiples coming very quickly. 2.1 billion users, certainly now we're getting closer to that number. 2 hours of video today, that's less than what people are consuming on television. And then the bitrate goes up to 7.5. Now we're looking at over 1,000 terabits, in other words, a petabit of streaming traffic. And these are not irrational multiples that we're projecting here. These are very, very practical and achievable ones. But the trouble is, our current infrastructure and the solutions we're deploying today are not scalable to reach that number by any means. So what's happening? More people are coming online. This is a chart of projections up to 2015. So right now we have about 2.5 billion people online. These are people with any type of internet connection. That number is projected to go up to where we're almost reaching saturation on the human population. At least people who can afford to be on the internet will be on the internet probably around about 2020. The infrastructure will rise to that level. And there's also more devices. You probably have a lot of internet-connected devices in your home. These are rising now. So we're not saying that people are going to be carrying, remember it was 5 million, not going to be carrying 10 devices each, but you might have 10 addressable devices that are associated with you. It might be your watch, your television, your home router, and your cell phone. So this is a brief summary of internet video. And you may remember back here in 1999, Akamai was the CDN that did the Victoria's Secret webcast. We were thrilled. We reached a gigabit per second for the first time. Promptly, our network fell over. The ISPs we were feeding fell over. But it was still a big success, we thought, because finally we saw video on the web. And it grew quickly from there. 2002, 16 gigs, Steve Jobs. And then it really jumped up. 2008, with that was Tiger Woods limping on the 18th, if you remember that. That actually drove a lot more traffic than the prior election did, up to 444 gigabits. But what was happening was both the volume of people online was rising, and the bitrate we were delivering then was rising as well. Up to the next election, we broke the terabit barrier for a single webcast for the first time. And I'm just doing Akamai traffic now. There's obviously other people delivering this content, but this is the portion we delivered, a terabit. Last Super Bowl, 1.4 terabits climbing. OK, that was 2012. What's happening is we shift this over, and we see that our growth is actually projected to grow dramatically. OK, this is not linear growth anymore. It's exponential growth. And this is just a marketing slide. But I want to show you the actual real numbers. So these are real network growth numbers now. This is the network growth for the last 3 years, showing peak traffic. So back in July 10, 4.6 terabits. And we got up till July 13, 15.4 terabits. So that's basically 100% growth. We're doubling the total peak traffic every year. And then what happened in this last year, boom, so much for our linear growth. Up we go. So we crossed the 20 terabit per second barrier. There's 20,000 gigabits per second across a network, the majority of which is video. So video is starting to dominate our network, just like it's dominating the internet in general. And the fraction varies. It's somewhere between 55 to 70%, say, and the number's going up. As the bitrate rises, as 4K comes out, as HD becomes more pervasive, SD fades out, so this number is climbing rapidly. So this is we can make projections then. So this is where Akamai thinks traffic goes. So this is all forward projection. This is January, where we are now. This is average. Okay, I'm not dealing with the peak. So our average is still under 20. It's probably going to cross above 20 pretty soon. But we're thinking by January, beginning of 1770, we're looking at providing 70 terabits per second. And this is not a crazy exponent here for this growth. Now, we cannot buy that much bandwidth today. We don't have private networks. Akamai operates over the general open internet, and we have to purchase every bit we deliver. We're also storing a tremendous amount of video in the cloud. You may not realize it. So today, January 13th, we're coming up on January 14 here at about 40 petabytes of cloud storage. And this is not cold storage. This is content accessible in, say, 30 milliseconds. It's warm storage. That number is growing up dramatically to the 200 petabyte range. So not only do we have to deliver this content, but we have to store it and then access it very quickly in a cloud network. This is another chart of real data. It shows the live video stream count. So this is not end users consuming. This is streams being pushed into the network. So 30,000 here, 60,000. This is a pretty linear growth, but this is only over the last year. So again, we've doubled the number of live streams coming in, 60,000 individual live streams coming in, each of which is being replicated tens, hundreds, or thousands of times. Or hundreds of thousands of times for that point. Now, I mentioned we're getting hits at the rate of 40 million per second. We store all of those, and we have some tremendous stats. So if you go to Akamai.io, it'll actually route you to an online site where we publish something called our State of the Internet report. And you can go and grab it. We publish it quarterly, and it contains a lot of very interesting data. So I want to look at one that is, I think, pertinent. It's average connection speed. The global average today, around the whole world, for all people connected that Akamai is distributing to, and we have a good general cohort when we take these stats, is 3.3 megabits per second. And that's from Q2 of 2013. So it's pretty fresh data. This shows the Americas, United States, which is where we are right now. 8.7 megabits is the average connectivity. That's come up a lot. And I notice a lot of your tests, you're testing content at 1 meg or 2 meg. But in fact, the providers today through Akamai, people are typically delivering video at 3.5 and are starting to inch up to 5 and even higher. So I'd encourage you to start doing your research at bit rates that are matching what the market is actually pushing people to do, because consumers can consume it. That's average. This is average peak connection speed. So it's the peak over a defined period. And you can go and read our fine term, because I know you'll probably argue over how we're taking this data, but we do define it quite precisely. The peak for the United States, 36 megabits per second. That's high. And that's going to show us a number of things, one of which is that the congestion on the internet is not really at the edge. It's not between your house and what you're connected to in your ISP. And it's typically where the ISPs interchange and peer with other ISPs where the majority of the bottlenecks are occurring. So again, from Akamai.io, it's an interactive chart. You can go pick countries and see how your country has fared. This is the last 7 years of data. And I just picked Japan, Switzerland, UK, and the United States to see how we're doing. And we've seen that we had pretty linear growth for 3 or 4 years, and now we're starting to rise in an exponential way. United States and Europe are coalescing. Japan, and I should have put South Korea on here. They are the leaders, actually, for throughput. But they're up. This is average, again, average connection speed well above 10 megabits per second. We look at the same data now, peak connections, and we see that the United States and UK, Switzerland pretty close in the 35 to 40 megabits per second, and Japan going up almost to 50 megabits per second. That is more than enough bandwidth to deliver 4K without any sort of optimization whatsoever, and that's the average. Another interesting stat we like to look at is what's the percentage of users with greater than 10 megabits per second. This is, you can think of from a marketing term, the addressable market. Again, the United States, 25%. Pretty much all these countries, certainly what we would term the first world, are well above 25%. That's a huge market. That is more than 100, just under 100 million, probably 80 million people in the United States, or 70 million people that you can drive significant amount of over-the-top content to. I like to take a global perspective. So this is a map of the whole world with that same data mapped onto it. Bright blue is good. So these are the countries that are above the 10, 20 megabits per second. The middle swath is dark. That's where bandwidth is lower. And I like to show this chart and then contrast it with this one. This is the GDP per capita. Okay, and you'll notice that they're very similar, that the bright blue here are the richer countries. These are the poorer ones. That corresponds very directly to what we're measuring with average connectivity. And this is a little aside, but I care about this because I come from this dark spot here, which is Zimbabwe, okay? And what you see is you basically get what I can call a connectivity productivity spiral. If you're in the United States, increased connectivity leads to increased productivity, and you keep going up. There's more wealth generated, more people can afford bandwidth. The opposite occurs in a country like Zimbabwe. Poorer can't afford connectivity, productivity goes down, and the gap widens. And I only say this because I have a chance to just encourage everyone to, when you develop applications for the internet, don't only develop them for the bright blue spots. This is also the densely populated region of the world. There are an awful lot of humans in here who would like to get good internet connectivity too. And they don't live in a world where there's 0% loss and it's under a 50 millisecond latency. They live in a very different world, but they're still relevant consumers. And I hope there's some research being done to really optimize to get the red countries here and the dark countries here into the bright blue regions, respectively. More data that's interesting. So this is looking at retransmit rates across our network. So we can't measure congestion directly, but as a proxy for that, we can measure how much we're having to retransmit. And this is broken out by continent. So down here, North America, and it's a little hard to read, so I apologize for that. But the bright green down here is North America. We're looking at 0.2% average loss. So it's not zero. There's always some loss in the network. But look at these continents up here. That is South America, Asia, and Africa. Here we're looking at 0.9, about 1.4 and 1.8% average packet loss, approximately. And these are significant numbers. I'm going to come back again to when I start saying, how can we address this problem? What can we do to build solutions that work well for this part of the chart? And not only right down here with our assumptions of 0% loss. And this is for fixed line networks, let alone wireless.
So the numbers have
Yeah, so some defense, I had to take the date of this off. I can only release so much data. My legal team said, OK, I can give you this slice, but we can't say when we took it. So yeah, they increased a little bit, but I can't tell you the year or when. I would like to as an engineer, but I also like my job. So there's no dates, but there are some numbers. And if you're interested in this data and you have a relationship with Akamai, I can probably release some under NDA that's more detailed if it's for research purposes. And this is retransmit rates with load, which is kind of interesting. Not so much for the load, because as you might expect, as the load increases, so the retransmit rate increases on the machine, but more for the diurnal variation. And what varies diurnally? It's bandwidth, it's consumption. And here we see that the retransmit rate very clearly is also matching in parallel the consumption. And you might think this is obvious, and it probably is. But we have data at a very large scale to confirm this. So as that increased demand for content arrives, so is the congestion associated with it going to increase. So yesterday, Jason spoke about the Google webcast, which is the world record for concurrent views, 8 million. And I prepared my slides entirely independently of his, so there's an overlap here. And what's interesting is we're all in the web world proud of reaching that 8 million number. And as he did yesterday, I pulled the Nielsen ratings, probably for the same week as well. But what CBS does on a Wednesday night without even trying too hard exceeds by a good amount what the largest webcast or OTT broadcast of all time can do. That's pretty significant. We in the web world are far away. We're far away from being able to service NFL, and certainly for the 600 million projected views for World Cup soccer, we're nowhere close. Nowhere close. We'll do an awful lot of views. World Cup, Sochi Winter Olympics will probably set a new traffic record, followed by World Cup next year. That is for sure. It's going to happen. But we're not getting close to broadcast television. We need to fundamentally change how we deliver content over the web to get to these sort of numbers. And I know we get all caught up in oh, we did a terabit, but a terabit is not enough. 20 terabits is not enough to get here. 70 terabits, we might start getting here. The bitrate's also going up. This is real data. The Xbox One reveal that Microsoft ran a few weeks ago. They were sending 8.9 megabit per second streams as the top representation rate. That's quite high. And they had 8.45 million views in the first 24 hours. That's not concurrent. It was spread over 24, but that's still a significant cohort. That's a cable rating right there. And that's typical of these larger events. A reveal or a sports game is reaching these bitrate levels and that volume. So we have what I'll call a bandwidth crunch. Greater volume, greater demand, plus more devices, plus more people, plus congestion equals crunch. Crunch is a non-technical term, but it means we have an impending challenge. And there's no single problem to this solution, and nor am I here to suggest that we have one. There's an array of technologies that can be used to solve this, and I want to take the rest of my time to look at 10 of them, and hopefully demo 4 of them if Friday the 13th permits. Okay. And we're going to go quickly through these and not in depth, but the point is to say, okay, now we see what the problem is, what can we start doing? So HEVC is probably top of everybody's minds, and people tell me, whoa, HEVC is going to cut your network traffic in half. Aren't you worried, Akamai? Because we bill by the gigabyte. That should be our revenue getting cut in half. So I don't need to talk more about it to this audience. Yes, you can get 30, 15%. Yes, decoding is complex, but we can do it on devices today. What's significant is HEVC, if it can get down to these levels, opens up new markets that you can't address. Your lower-end ADSL and DSL subscribers today, people at 1 megabit and below, are not getting good 720p at, say, 500 or 600. But as we shift codecs, they can. So we might take bandwidth away on our upper-end streams. You're going to be adding a lot of new subscribers in at the lower level. What I just said there. It also makes UHD and 4K feasible. Remember, I said the average bitrate is 8.9. So already we can deliver. I'll show you. Well, let me get to this next slide here. Major issue with HEVC today is the legal and patent issue is still not being resolved. I know one very large company, I can't release their name, has been told to stop work on their HEVC initiatives because of the unstable licensing situation. They're a company large enough to lose a lot of money if it goes the wrong way. So HEVC is only going to address this problem if we maintain quality parity and we use HEVC as we swing our sword to cut the bandwidth. But HEVC can be used equally to raise the quality and keep the bandwidth the same. And that's the way I believe most people are going to use it. It's this, what happened when we went from MPEG-2 to MP4 on the internet as well. Everyone said MP4 is half of MPEG-2. Bandwidths are going to drop down. They didn't. They went up, they had a little jiggle, and then they rose up dramatically. Okay, and the same thing is going to happen here with HEVC. I also wanted to point out that H.264 can be optimized. Yes, it's a mature codec, but these companies down here, if you go to their sites, they will say that they can achieve H.264 30 to 40% less than, say, X.264, which is we can use as the baseline. And it can decode on existing appliances, of which there's a huge population. And that's a fundamental change. Why take HEVC for 30 to 50% with a legal risk and without hardware acceleration on the device that's playing it back, when you have an option to use H.264 in a mature ecosystem with very clear license environment and achieve maybe 30 to 40% bandwidth gain? So the whole point here is that H.264 has a lot of legs left in it. I'm not writing it off anytime soon. Also significant, Firefox this week adopted VP9. So as we're looking at HEVC, the fact that Chrome and Firefox can support it is a real boost for Google. Because up till now, it's just been Chrome, and it's been a little bit of an island. We don't see very much traffic for VP9 on Akamai at all. Would I like to see more? Yes. I would like to see whatever gets OTT content to more subscribers. Device compute capability is rising. So this is a quote that I'm not sure who said it, and you've probably heard it enough times. The cell phone in your pocket has more computing power than all of NASA had in 1969 when it launched Apollo 13. Maybe true. A lot of people will argue that, hey, the navigation computer in Apollo was a PLC basically dedicated to doing one thing. What I have in my pocket is a very generable and flexible device. But you can't deny that it's fundamentally more complex. And as an aside, as an aerospace engineer, I look at that quote and turn it around, and I think, wow, they basically had slide rules mostly back in 1968, 1969. They got guys to the moon using slide rules and a PLC. So I think the engineers were incredibly smart then, and I think the astronauts were incredibly brave to trust them. The PS4 of today, which costs $400 or so, unless you got a coupon, has the power of a military supercomputer back in '97. For me, '97 seems like yesterday. This is pretty undeniably true. The compute capability of gaming consoles, at least, has risen dramatically. Quad-core is the norm. I have a quad-core in my pocket. You probably do too. Octa-cores come out. I don't know what we're going to call dodeca-cores or what we'll have next year. So why do we care? Why does this affect media? And the real answer is that we can decode ever more complex compression schemes. There was a paper yesterday on exactly this subject, how to take advantage of some of the power in the decoder to improve the scheme. And this is going to increase. We will have a successor to HEVC, maybe H.266, and it will require more complex codec, and it will be more efficient. This is undeniable, and this will start to address the problem. So 3, storage density is growing faster than compute ability. And I made that word up. I don't think it's a real one. So this is basically megahertz versus time. Did you know what the blue line is? It's Moore's law. Okay, that's the increase in compute cycles over time. But do you know what the pink line is? It's something called Krieger's law. He was the CTO at Seagate, and it's the rate in our basically storage bits, our storage bit density over time. Look at how steep it is compared to Moore's law. It's huge. And this is a log scale, okay? So haven't done the math to figure out if that's twice as steep or, in fact, much more steep than that. You can probably tell me. But a tremendous growth in storage density. Anyone recognize this? Yeah, it's a flash drive. It's Kingston's flash drive, but it's a 1 terabyte flash drive. So this is 1,000 gigabytes that you can now lose in your pocket. Okay, you're smart. Okay. And why should storage affect bandwidth? So in my world, much like you can say E equals MC squared and they're versions of one another, storage and bandwidth, you can trade off. If I can store something locally, I don't need to deliver it. Okay? The more we can store, the less we need to deliver. Yes, you need to get it there in the first place, but that's a different problem. And this is a note to remind me to tell you a story I had back in 1999, and it was the dot-com boom in San Francisco. Mark Andreessen, the Netscape founder, was on stage, and he had a little Nokia clamshell phone, and he held it up, and he said, imagine a future where, because we were talking about streaming audio to the phone back then, and we're hoping to get audio out of 56K. And he said, imagine if all the songs you ever wanted to listen to were already on your phone. And if you wanted to listen, all you had to send is a key to decrypt one, and then you could listen to it. And everybody laughed. But today, this is entirely feasible. My phone has 32 gigs on it. That is, my entire audio library is like 6 gigs, and that's a lot of music to begin with. So pretty much you could buy a phone that had the songs that most Americans would ever want to listen to. It could happily sit in the phone, and if you wanted to listen to it, you could just send the authentication token, you pay for it, and you could listen to it. So that has come to pass. Now, what if your home router had a 5 terabyte drive inside it? It doesn't today, but a 5 terabyte is not that expensive. But if you take a 3.5 megabit per second movie, 90 minutes long, you can fit 2,500 of those on a 5 terabyte drive. Single bitrate now, because you don't need to adapt, because it's in your router. And that certainly covers most movies Americans are probably going to watch, at least the short tail, or 80% of them. So it's not infeasible that we can start to move storage closer to end users and take advantage of Krieger's law. It's saying that it's becoming so cheap to store stuff that we should take advantage of and use that to offset the need to move content to these devices. Right, multicast. Majority of traffic, and probably all the traffic over Akamai today, is unicast, HTTP over TCP. And I know we have Octoshape in the house. They will say, hey, we're not, and that's true. So there are certain exceptions to that, but certainly from Akamai's perspective, it's all unicast. IP multicast, the trouble with it, it's enabled per network. So it has different configs. I can't push out one stream that is universally acceptable. I know there's standards for this. The trouble is they don't get implemented in exactly the same way. And that's why you don't see a universal multicast over IP solution. Multicast in the long tail is also inefficient. It basically, if everyone's watching something different, it's no better than unicast. So what's it good for? It's good for live sports events, news events, linear marquee programming, so, prime time, and maybe the top 100 Netflix titles if you carousel them in some sort of solution. So it does have strong benefits. Instead of sending 1,000 streams through my ISP, I can send one and have them fork it. So Akamai is interested in multicast. So we said, OK, if we're going to do something with multicast, how should we do it? What are our requirements? It must work with our existing ingest system, must work with DRM, must work with targeting and authentication. It must also support existing players, meaning it's got to work on an iPad. We can't go and expect Apple to deploy multicast. We've got to do something to enable it to work there. It's got to support adaptive bitrate. It's got to support DVR or time shifting. It must also be format agnostic. It mustn't require a specific format. Today, the majority of our traffic is HTTP, chunked formats, HLS, HDS, MPEG-dash. So we actually have a research project around this. It's not a product. I must make that clear. It's research. I'll explain how we intend to do multicast, at least in our labs. And it's a little bit of a complicated diagram. We have encoders pushing in content. We segment our media on the fly. So the edge is doing the encapsulation and the packaging, generating, in this case, an M308 manifest and TS segments. We have a multicast delivery controller that is subscribing to that stream. This is a segmented file-based system and converting it to a series of multicast channels. These then move through multicast-enabled networks until they hit a router, till they can't go anymore. And then we take advantage of AMT, automatic multicast tunneling, which can take this multicast stream and tunnel it essentially through UDP between a router and a gateway. We're going to provide the gateway on the client. That client will then extract the file objects and present them to the media player on the device as if it had done an HTTP GET request for this content. So a fair amount of complexity, but this solves the problem because today we cannot reach our end users with multicast all the way. So we need to go as far with it as we can and then have a solution that can fan out and still reach our devices. Now I hope to demo this to you. We've never actually demoed this, so I'll see if it works. So, and I'm doing it on an off-the-shelf iPad. There's nothing special here. We're running our software, and I hope I'm still connected. And I'm going to select multicast. And let's see if I have bandwidth. OK, I have a black screen for Friday 13th. Let me just kill my app, come back. OK, I may have lost connectivity on my laptop. Let's check. Thank you, Cisco, for logging me out. And now I have to, in front of the entire room, type in a complicated password here. So, stand by. Lowercase 6. Tell me if I type something not right. 6, lowercase w, uppercase Q, 6, Q. This is the password now, anyone can have it. Y, Z. Yeah. Yay. Okay, I think we're logged in. Now we can try our demo again. Yes, okay, so the problem was connectivity. Now this might be a little underwhelming. It's video in a rectangle, okay? So let me explain why the video in a rectangle is important. So what's happening is we have an encoder pushing in a live stream into Akamai. We're generating a M38 manifest. This is playing off a stock standard iPad. And it's being pulled in by Akamai. We're subscribing to our own stream, converting it to channels per multicast. And this way, we're using a solution we call channel per chunk. So because we want to find DVR capability, and say we got a minute of DVR and we got 3 bit rates. It's 700K, 1.2, 1.7, just for demo. So we have 3 bit rates, and then we go back in time 6. So we take 18. We have 18 channels available on the multicast stream. And the client is intelligent enough to know if, our client is intelligent enough to know that if a segment is requested back, it knows via the addressing scheme which channel to subscribe to. So I'm glad it's working. You'll see more sophisticated demos coming out. But if this is a little view into the future of where we can start going with this, when this research work comes out of our lab and into the real world. And I'm going to do more demos around this later, with this app later, so I'll just leave it there. Okay, number 5, MPEG Dash. I am a big fan of MPEG Dash, spends a large part of my day working on it. I work with a number of guys in this room on that. Normally for people, this is a reveal slide. I talk about MPDs and adaptation sets, representations, and segments. I'm not going to do that for this audience. I'll get to the point. Why is MPEG Dash going to help solve the bandwidth problem? It's really all about focus. Okay, you'll notice that the majority of the papers delivered here today reference Dash. That's important because the work is being done and the thinking is being done around Dash. And the work done here is what bubbles up and becomes product in a year or two. And it's going to make a stronger Dash product than an HLS product or a smooth product or an HDS product. Okay? So by all of us, both the encoders, the CDNs for delivery, and the player builders focusing on the format and not having to spread and dilute our effort across multiple competing formats, we can make a better solution. So I'm a fan of Dash for that. A shout out again for the Dash Industry Forum. This is a group of companies who get together to say that Dash, the paper spec, is just that. It's just a piece of paper. Okay? We need to turn it into something useful in the real world. So this group sits around making Dash useful. And I encourage you to join it. You can join it for the lowest price if you're in an EDU associated with the university, or if you don't make any money. It's easy to join Dash Industry Forum. And you can work on groups that are helping to change it. It's a direct vector. You don't have to be on the MPEG committee. We have enough people on the MPEG committee here that if you want to get changes made, you can work through this group to do it. And we're also addressing, we have task forces with things like advertising insertion. I promise you the big companies are going to, when the first thing they come to Dash, they're not going to worry about the latest adaptation algorithm. They care more about how they can inject ads reliably into that stream. And that's something that needs to be solved here. So I'll do a quick demo of this. And I'll also use this demo opportunity to talk about another technology that I think is beautifully integrated with Dash at the same time, assuming I've still got bandwidth here. Okay? So what you're looking at is a JavaScript-based player. This is a Dash.js project I started on GitHub. Dash Industry Forum has now taken it over. It's an open source player to play back MSE and EME-based streams. Because you can't hide your logic anymore. It's all there in JavaScript. Okay, so if we can't hide it, why don't we get together and collaborate and make the best possible JavaScript-based player to do this? This is what this project did. It's BSD3 license, you can use it. So I would encourage people who have adaptation algorithms, come in, that you can easily, the adaptation logic is neatly encapsulated here. You can substitute your own. I would love you to come in and replace what we have right now with a better version. If people keep doing that, this can become the baseline for some fantastic playback. And if you've been building video players like I have on different environments using Flash or native players for the last 10 years, you'll appreciate how beautifully simple being able to write a complex player in JavaScript is, how quickly you can change it. I can give a different player with different rules to different people at different times of day. And I haven't been able to do that before. And I can play 4K content through this. I was going to demo that. I have a 4K feed. It plays nice, but my little MacBook Air doesn't like 4K size, so it struggles. But it's not the fault of the format. I just need a more powerful machine. So I'm very bullish on this solution. I encourage you to look at this project on GitHub, dash.js, and contribute and collaborate with us. Let me cut the noise off. We pause for a comment from Ali.
From time to time in the HIF meetings, we actually put the clients from different vendors into test.
Yep.
So you can actually bring your own adaptation algorithm or whatever, and
that's true.
Compare it with the other companies' clients. So
we have bake-offs between players.
Yeah.
And this one does all right, but it's a collaboration. And if I scroll down, who's submitting code to this? Digital Primates, Microsoft, Google, YouTube, Akamai, and Toil from India, because we put up everybody who contributes. We've actually got 13 committers right now. But the point is, there's very big companies involved in supporting this project. Okay? And we would love to have alternate adaptation solutions in it and make them easy to switchable and to test out.
There's a question from the audience, actually. Is Red Bull our sponsor so that you have their video?
Red Bull are not our sponsor. That is content that they allowed Akamai to use for Akamai promotional purpose that was encoded by Invivio, and it's their bug on it as well. So they're not a sponsor, but I do like Red Bull. OK. Number 6. Improve existing TCP. So Akamai bought a company called FastSoft last year. FastSoft's a TCP congestion avoidance algorithm, targeted at high RTT lengths and lossy conditions. It uses queuing delay instead of loss probability as the congestion signal. And we acquired the technology, and we deployed it on our network. And it's a great fit for us because it's unilateral. You can apply it on the server side, and it works with the existing client. And we got some fundamentally great results. So after deploying this on our network, without changing anything on the clients, in Europe, we had a 22% improvement in throughput. And here in the United States, with the North American service provider, 15% improvement in throughput. That's a huge change. For us to get 22% more out of our network is probably $40 or $15 million of new machines we would need to deploy. But it was done with a software change only. That tells you, it speaks to the incredible power of software. And then we sort of take TCP for granted. We're still using Reno as our standard congestion algorithms. And I'm going to show you some data. I'll show you data later on Reno versus fast TCP. And you'll see just how much better fast TCP is compared to Reno under conditions that have some loss or higher latency. And that's relevant because you remember my slide going back earlier. Not everyone in the world has low latency and zero packet loss. Number 7, caching networks. I mentioned before, what if we had a world where all the content we wanted was one hop away from us on the server? That would solve the congestion problem, because all the congestion is around moving stuff from one side of the internet to the other. But if it was already available close to me, I wouldn't need to move it in the first place. People make a joke. What's the fastest way to move 10 terabytes from San Francisco to New York? Huh? By train? Almost. Yeah, pretty much. Well, fill your suitcase with hard drives, get on the red-eye flight, and fly there. The throughput of that connection, even though it might take you 6 hours and 2 hours on either side in the airport, is still greater than anything we can do with fiber optic today. So we can do that. Think of caching as free delivery. We certainly do. It's our business. And the more we can cache, the less we have to get it there. The trouble is there's not infinite cache footprint. In fact, there's strong cache contention. We have 3,600 customers. All of them want their content to be on each cache. We can't put it all there. So we have to figure out what goes there, and that's a big problem. But caching removes origin and midgress traffic. Obviously, you can't do it for dynamic content. You have to go back to origin. But there's a large part of each site, and certainly for media, it's not dynamic. Once I know what my media asset is, I can repeatably deliver that content. Caching used to only exist inside CDNs. Now we see telcos and major ISPs starting to build out more sophisticated caching. Again, I made my slide before. Conveniently this week, Verizon bought Edgecast just to prove the importance of this point. They're building out a caching network within their network. Akamai is doing the same. We have a whole network division now that we've built up. Akamai used to be it's sort of us or nothing. And now we've realized that our future is intimately tied with the tier 1 providers. And so we have a division that has done deals with AT&T, Swisscom, Orange, and KT, and there's more in the pipeline, where they can actually manage our software. They can license it, they can run it, and they can use it for their benefit, but they also get federation of that content outside of their network, and that's a big deal. So people are being far more intelligent about really, really milking caching for as much as we can. I don't say milking in a bad way. I should say optimizing it. Caches are inching their way towards the cell tower, which is sort of the wild west of caching, because it's not an IP network between your phone and the tower, and it's been very difficult. We certainly would love to put caches there. We struggle with that so far. But everybody is trying, and I think we will get there. The closer we can cache content to the tower. Another solution is, well, what if there's other ways for the phones to talk to each other? What if, say, in this room, we could use Bluetooth to share this webcast with our phones, instead of all of us having to go to the Wi-Fi access point and cause congestion? There are technologies that exist for doing that today, and they make sense. 8, hybrid 8 UDP TCP. So I mentioned that 95% of all OTT content is unicast HTTP over TCP. Now, UDP offers higher throughput, but it doesn't correct for congestion, and it doesn't play well with other TCP flows often. UDP is like the big bully that goes to the TCP party and eats all the cake. Yeah. How can we improve this? So what if we created a new hybrid protocol where the initial request from the client to the server was HTTP, but the payload, if it could be returned via UDP? Okay? So this needs to be transparent. It needs to work through existing infrastructure, because we can't expect the intermediate internet to change. For congestion control, we can use the fast TCP that I mentioned previously. It's a really good job at doing that. And we need some forward error correction in there as well. But if we put all that together, we have a research project at Akamai called Astraeus that implements this. So here's a chart from the labs, again, of Reno, which is our standard congestion control, versus fast TCP, the one I mentioned previously, versus Astraeus. This chart runs from 0% loss to 0.5%. Okay? So we're looking here at North America in well-connected cities. If you're on Comcast or Verizon Fios, this is your world. So we see that Reno is actually good. For 0% loss, it's doing better than these algorithms. And these are opportunistic, so we can turn them off. When we say we got low latency, we'll just go with Reno off the shelf. Okay? But notice very quickly, even at 0.1%, we're improving on Reno to the point where at 0.5%, which you can get fairly common even in North America, we're 14 times faster than Reno. And now we're talking about Astraeus, and we're 1.5 times faster than our own fast TCP. And that's a big difference. 1.5 times faster means you're watching the highest rendition instead of the lower rendition on adaptive video. If we extend this chart and now look at packet loss from 1% up to 10%, now we see that Reno is really struggling. We're 18 times faster than Reno at the 1% mark. And again, remember my map of most of the world. Most of the world is above 1% if you're looking at human connectivity, not IP endpoints. Okay? So we can really make a difference. Yeah, we can give 18 times better throughput there. So again, I want to demo this. So I have my same app up here. Let's do a bitrate test, see if I've still got bandwidth. So the first thing I'm going to do is play video from a server we've set up in Atlanta, Georgia. And we've added to the server 1% loss. Okay? And I'm playing back again through a standard iPad using the native player. We're playing an HLS stream here, 10-second GOP, 10-second segments. So our max available bandwidth, you can see, is being measured at 1.6 megabits per second. And of that, Apple's choosing to play the 1.1 meg stream. This is pretty standard. And I'm going through the Wi-Fi here in the conference room. There's nothing special. We're going straight through. Okay? So we're playing, and we had a little bit of rebuffering there. Now I'm going to switch over on the same device through the same Wi-Fi network to the same server with the same induced loss using Astraeus. Okay? Our max available bandwidth is now 18 megabits per second. A huge, huge increase. And our max selected bitrate is going to climb up accordingly. It's already at 5 megabits per second. So I've fundamentally changed the user experience on this iPad for what they could consume. We're playing 10 megabit per second stream. And if we go here, it should summarize those results. So our max selected bitrate was 8 times higher under Astraeus. For the conditions I have here at Cisco, the max available bandwidth was 10 times higher, and Astraeus didn't buffer and HTTP did. And that was with 1% loss. So you can say, well, repeat this test afterwards with 0% loss and see what it looks like, and I will show you that. But 1% loss happens more than we think it does. And certainly at 1% loss can make a huge difference in Asia, Middle East, and Africa. So just, again, a side note, Akamai Client. You think of us as a server company. You think of us as we are the guys who put servers in the cloud. But you've seen that we can do this hybrid HTTP UDP acceleration. We can do multicast delivery now, even though it's, again, neither of these is a product. We can do intelligent prepositioning, another word for caching content on your device. And we can do peer-assisted delivery. We have peers. So maybe we can add in a core services, we can add in a cache, and we can bundle all this up, call it client-assisted delivery, and create an SDK. And it can be our mission is to put that software on every single device out there. And that is our mission. Okay? So we are going to be the server guys, but we also hope to be the client guys and start intelligently leveraging some of this performance on the client side to improve the throughput. Number 9, fiber and transit capacity increasing. Again, this is one that we're not involved with, but we're directly affected by. The hop to your house is not where congestion's occurring. I heard a wonderfully accurate story where someone was commenting that getting Verizon Fios or fiber to your house and expecting it to improve your overall internet browsing is like widening your driveway and thinking it's going to reduce your commute time to work. Okay? It's not. And it's a wonderful analogy because when you drive out your house, it's typically not congested. You drive down a road, where do you hit congestion? When you hit the highway. And the highway is essentially the peering point where all the traffic's coming together and getting routed. So the congestion is not there. The congestion is between these centers. Fiber throughput has increased dramatically. Dark fiber's getting activated. What I think's amazing, NTT back in 2012 over in Tokyo, they demonstrated transmission of 1,000 terabits. That's a petabit per second over a 52K length of optical fiber. That's enough to transfer 1,300 or so 10 megabit per second videos in 1 second. Tremendously fast. So when people say, wow, OTT has no chance ever of replicating broadcast content, yes, we have. That's one fiber. We can lay a lot of fiber and we can start moving that content. And as a cynic, you might argue that 52Ks is not that long. Most internet traffic's probably routed longer. So Alcatel-Lucent in July in France showed 31 terabits per second over 7,200 kilometers of single fiber. 7,200 Ks is longer than the longest trans-Pacific undersea cable. Okay, and by the way, 31 terabits is 1.5 times the entire capacity of Akamai, as I just mentioned. So phenomenal throughput coming from fiber. So again, the backhaul, the long haul, is probably going to be fine. We still need to do work around the peering and the transit between the networks. That's where the congestion will occur in the future. And it's also not occurring at your house. You have more than enough bandwidth to talk to your ISP. And the last one I'm looking at, 10 is peer-assisted delivery. So I don't need to explain it as a architect. It's a very efficient architecture. It scales with the load, which most of them don't. Unfortunately, file sharing gave P2P a bad name. You walk into Enterprise America and you mention anything to do with P2P, and they're going to BitTorrent and Napster, and it's embarrassing. So Akamai has had P2P for 5 years. We don't sell a lot of it today, mainly because of the bad perception. But I think that's going to change with time. There's not enough pain felt in the unicast world yet, but the pain is coming. It's certainly coming. Those charts are going up. And then we're going to start looking at peer assist. You do need overlay security. You do need a control plane. And it's also challenged by an asymmetric last mile. I can download 8 megs happily on my Comcast connection, but I can't upload 8 megs. That means I have to get 3 or 4 peers in order to feed one new peer, and now my peer offload rate is down at 20% at max. And that's also not efficient. So it's great for audio. We can happily P2P, and a lot of the solutions you see today work very well for audio. They also work very nicely with adaptive segmented delivery. It's a beautiful fit for P2P distribution because I don't care. I can get my little blocks from different sources and I stitch them together in my client. I don't have a dedicated RTP, RTMP session that I have to contend with. The barrier to deployment has always been installing that executable. That's why it never really took off on Macs and PCs. People didn't have admin rights, or it's just a hurdle to restart your browser. In some cases, restart your machine just to put a P2P client in there. But two things can change that. What if the peers weren't exactly on your device, but they were very close to your device? Okay, what if they were the TVs, the home entertainment, and even your refrigerator? And people laugh when I say refrigerator, but it's a big device. It's a high-priced unit. Lots of room at the bottom to put your 5 terabyte spinning drive. It's always got power. It's got great connectivity, the same connectivity you have in your house, and it's got cooling. Okay, and if you think that Samsung don't have a lab where the refrigerators have hard drives in them, you're wrong. They do, and it makes total sense. And that could be the peer. That's a great peer. And then there's not that much congestion between that. There's some on the local Wi-Fi, but not enough to stop you enjoying 4K content. And also, I think WebRTC, and I'm talking about data channel side, not video channel. Data channel with WebRTC is also, as an architect, a beautiful coming together of some technologies. Combine that with Dash. And I think the guys at StreamRoute in France have done a great job, and I want to make that my last demo. They are not affiliated with Akamai in any way, but I think they are demonstrating the power of this solution. So let me switch over here. You can find it demo.streamroute.io. So we're going to start playing content, okay? And notice I didn't install anything. I just went to my browser page under Chrome, and content starts playing. I'm going to turn the volume down here. Okay. And already I've found a peer. I'm connected to 4 peers without doing anything on my machine. So the chart over here is showing my peer throughput, and the traffic from the server is down here at 12. What I can do is spawn more windows, and if I take this down here, I can even peer with myself, okay? And as people who handle video delivery, to make it this simple, this easy, and this pervasive, there's 100 and I don't know how many installs Chrome has right now. The Google guys can probably tell us, but it's well over 100 million. I have 100 million clients that if they all watch a World Cup football game now, there's a reasonable chance we could make this work today without changing anything in this demo. And StreamRoute, I think, has just done a deal to do a 4K distribution for World Cup soccer with France Television. That's a big deal, and that's a fundamental change in how we deliver video going forward. And it's enabled by WebRTC. It's enabled by MPEG Dash and segmented formats. Shut these off or they'll suck up bandwidth. Okay. So there's many more than these. I didn't have time. What's going to cause more congestion? 4K video. 4K is coming. People think it's another 3D. It's not the same. 4K is, it's hard for the television manufacturers not to sell the bigger devices. And when they're there, it's going to be hard for companies not to service them. We can also have enough bandwidth today to service a good fraction of these devices, at least enough to drive the market. Screen resolution is also rising in our little phones. And it used to be that we could send them 360p video and upscale it, it would look fine. The trouble with your phone or your tablet, you're close to it. And when we start putting 1080p screens in, and I even saw a 4K demo tablet, now we need to send more bandwidth to each device so it looks good. And then on the other side, what are the optimizations? Didn't have time to. Speedy, HTTP 2.0, quick from Apple. Server bits per watt is increasing. Pre-caching, in other words, guessing what the user is going to consume, pushing it to the device. There's a lot of solutions out there that are working towards that. Residential fiber, software-defined networking. We saw the demo last night. That can make a big change in solving that interconnect congestion problem. And then wireless Wi-Fi offload and multipath transit for TCP. So the bandwidth crunch is a big problem, but it's an opportunity for those companies who choose to address it. Akamai is certainly one of them, and we look forward to the challenge. So I want to thank you for your time this morning, and my witch and I will take your questions.
All right, thank you so much. We have some time for questions. Yes, sir.
Excellent talk. Okay.
Yeah.
So I was wondering what's Akamai's strategy to support 4K, 8K content down the road? Is there any, from technology point of view, is there anything special to deal with that?
So no. So I'm running our 4K initiative, so I'm glad you asked that question. We're happy to do 4K today. So there's one great thing about Akamai. Our network architecture is highly distributed. We don't have big data centers filled with servers like most companies do. The biggest thing we have is called a region, and it's about the size of your office, maybe filled with 100 or less servers or a few more. Yet what we have is we have those regions in every single ISP in the world. We have thousands of regions, highly distributed. Our goal is to get our server within 20 milliseconds or less from you. And you can ping an Akamai address and see how far away you are. It's mostly that low. The advantage of the low RTT is the throughput is higher. And that's always been our game. So for delivering 3.5 megabits per second across the country, so the 100 millisecond RTT, you can do it today. But it's much harder to deliver 12 or 15 megabits per second. But because Akamai is closer to you, it actually works well. So I have demo. If you're interested, I have a bunch of 4K files. We have Big Buck, or not Big Buck Bunny. We have Tears of Steel in a 4K on our network. You're happy to test it out. Our stream packaging works with 4K, meaning you can put in an MP4 file. We will dynamically synthesize HLS and HDS segments out of it and give you adaptive bitrate. So we're very bullish on 4K. 4K is a great uplift in terms of throughput. The network can sustain it, and our architecture is well positioned to support it.
I see. So can you elaborate a little bit more on your collaboration with Korean Telecom on in-network cache?
So I'm the wrong guy for that, but we have a whole Aura network division that handled that transaction, and I can get you more details.
Okay, the third is, what's roughly the timeline for you to roll out your HTTP and UDP hybrid solution?
I was told not to give any timeline, or again, I lose my job. So I wish it was tomorrow. It's not. It will happen. And when it happens, we have a big sales force, and you will know about it, probably more than you want to. So it will come, but I'm not able to give a date for that. It's just today, it's just a research project. And it's not a commitment even to a forward product.
Okay, thanks. That's all.
Jaeyoung. Oh.
Yeah, please.
Hi, Will.
Hey.
As a C device manufacturer point of view, so we are highly interested about the 4K delivery in the internet.
Yep.
But could you think in the adaptive streaming format is still working in the 4K delivery, because in quality degradation or adaptation is very sensitive things is for in the 4K display point of view. So even if we can make it optimal, is so in the segment format, but still, if its end user can recognize there is some in the change of the quality, so that is it's a key issue for in the Samsung. So,
So I think the question is, as we go to adaptive delivery of 4K content, it's very disconcerting if you're on your 4K monitor and you switch, say, out of 4K to an upscaled 1080 or even worse. So the answer there is that if you're delivering a 4K feed to a person, firstly, you're not going to have adaptation sets that are not 4K. So your lowest, you might do 4K at, say, 10, 15, and 20 megs per second with unoptimized H.264, and maybe at 6, 8, and 12 with HEVC or VP9. So you can stay within a 4K, so your changes will be less. But you might also, you can use, say, a dash MPD to define your content, but you can build a player that never switches. So it doesn't adapt. It just picks, say it makes a bandwidth test and it commits to one bit rate, because there you've decided that the quality change from one to the other is too much of a penalty, to use the Markov process, too much of a penalty compared to avoiding rebuffering. So you might be very conservative and just pick a bit rate from that set. So I see people doing that first. Some people are also doing just a single progressive download as well for MP4. And I have some examples. So if you want to test, I have both segmented and MP4s available on the Akamai network, and you can see how they perform on Samsung devices and see what that switching is like. And we're interested in working with you on that.
Before the next question, actually, I would like to ask whether these demos are actually available somewhere on the web, so that people who missed the demo can go to those websites and try them out. So
StreamRoute certainly available on the web, because it's not mine. The Australia stuff, certainly not available on the web. And it's, again, not a product, so we can only show it under controlled situations.
Okay.
And then MPEG Dash, available on the web, yes. Dash.js, go to dashif.org, go to the players section, click on it. So that's available.
All right, cool. Yes,
Okay,
Aurelio.
my question is on fast TCP. You said that Akamai is using fast TCP as a standard TCP for delivering to all the people.
So we've installed it on our machines. We don't turn it on for all traffic, so we turn it on for mostly our media traffic. And we've got to be careful about turning it on in situations where it's not going to perform as well as Reno, which is very low RTT and low loss.
Because we did a lot of study on fast TCP, and we knew about a lot of weakness of this fast TCP. No? So I'm surprised that that could be the standard. I could imagine that you were using, for instance, to transfer a large amount of data between a data center to another.
And if you look at the test delta I showed, it was for the transferring of a 40 megabyte file. So I think that's a case where fast TCP does well. And we have the ability with each connection to use fast TCP or not use fast TCP. So we can turn it on in situations like large file downloads, which is also a big part of our delivery.
You decide on it per client basis? Or per
We
connection?
decide on a per delivery
Per
config,
delivery.
if
Okay.
that makes sense. We have something called CP codes and hostname config, and we can turn it on for that particular config.
Is
So
something available, some document on this available for public?
I don't think so. It's basically an internal solution. We've turned it on.
Okay.
And also, we hired all the fast TCP engineers worked for a full year on it before we deployed it. So what you had tested before may not be the exact version that Akamai has deployed.
Right.
So the combination of hopefully we've improved it, and B, we're using it where it makes the most sense and not just blindly everywhere. I'm not claiming that fast TCP is a solution to all problems, but it certainly is a solution to 40 megabyte downloads over high RTT.
Okay, thank you.
Thank you. Yes, sir.
I'm wondering about the quality. So maybe you can say a few words about how the quality as perceived by the user especially impacts your streaming and content distribution strategies.
So user perceived quality. Again, we distribute what our customers choose to use. So the question is really, is the quality affecting a customer? Because that's going to affect what the customer. Akamai can only suggest people encode at certain bit rates, but it's up to the customers what they encode. Our transcoding solution will prepare content from 200K up to 8 megs as a default. I think in general, people are getting far less tolerant of poor quality on the internet. Akamai did a big study with data on our real, again, over hundreds of millions of users. And we did the study that shows the abandonment rates as a function of the startup time and the rebuffering ratio. Much like Conviva were presenting yesterday, we see the exact same pattern there. So we see users becoming less tolerant of those exceptions. And we also see the ecosystem rising to the challenge. We are getting a lot less buffering. We are getting a much higher quality. There's not many videos you probably look at on the web today. You think that's poor quality. Usually it's good. I don't know if that answered the question.
Yeah, sort of.
Okay.
And the burning question for most people here actually, can we access some of that Akamai data to do some research on it?
So I'm as an engineer, I would love to give data. I don't have the data, but I'm happy to put you in touch, anybody who wants it, with the people who do have the data. Our big problem is customer privacy. We have very strict rules. And if we release data, say logs, it's got the file name. And there's a lot you can extrapolate from that. So that's been our real blocker. We would have to anonymize it in order to release it. And to date, that's a big project. We can use it internally for ourselves, but we haven't been able to release. So the biggest blocker, and rightfully so, is privacy.
So you guys all know who watches what around the world.
No, we don't. We don't know who watches what because we don't mine our logs for that. We mine it for what did we deliver for billing. And we also look for loss and retransmit, and we have media. But our media is all collected by clients. So we have a large collection system called Media Analytics that can take millions of current client QoE measurements and feed them back to our network. And we're not doing that by log analysis. We're doing that by client reporting.
I see. All right. I think one last question over. Yeah, Thomas.
Yeah, broadcasters are considering for 4K looking at higher luminance dynamic range, a wider color gamut, as well as higher frame rates up to 120 frames per second. Is this something that you're looking at as well?
Certainly. So this discussion's come up more, and people have a vote. What would you rather have? 4K video with current luminance and color space, or 1080p with brighter luminance and better color? And all the people at SMPTE certainly put their hands up and say, we'd rather have 1080 with improved color gamut. But those are broadcast engineers voting that way. And also Consumer America loved YouTube because you could push it big at 360p and it's, wow, it's full screen video. It was awful. You could see the macro blocks. So the general consumer is different. I think they don't appreciate what color and luminance can really do. I know Dolby's doing a lot of work with HDR for video. I've certainly seen some very compelling content there. It's Dolby are trying to do for video what they did for audio and multi-channel, and there's a lot of interesting parallels there. So certainly, again, from a delivery side, that doesn't affect us because it's a binary object. That the luminance and the color gamut is a function of how you encoded it. To us, it's a binary object, and we need to get it reliably from one part of the internet to another. So we're all for different flavors, whether it's 8-bit or 10-bit. I think that's going to be driven by the hardware that can play it back. And the nice thing about something like MPEG Dash is you can put a laundry list of available content in there, and the client chooses the right one. If it's not 10-bit, it'll pick the 8-bit. And that's, from a CMS point of view, that's also a much more flexible way than other solutions which assume that the client can play everything you're describing in the manifest. And Dash doesn't make that assumption. We're at like -2 minutes.
Yeah. All right. Thanks again to our speaker.
Thank you.
Thank you so much. We have to come.